You're live.
All right. Good afternoon. My name is John Crighton, and I'm the Chief Technology Officer at Crighton Solutions, where we're working to implement agentic AI to improve the efficiency and effectiveness of our electronic health records platform for hospice workers. As part of this process, we've been investigating AI agent protocols. AI agent protocols are a common language for multi-agent systems to communicate between heterogeneous agents. They're like HTTP for AI agents. Previously, interactions between AI systems were framework-specific, ad hoc, and lacked standardization. They were like private chat rooms where each participant was speaking a different native language. This made interoperability difficult, inefficient, and complex to integrate across diverse systems. The new protocols solve these issues by providing a standardized, common language for multi-agent communications akin to HTTP for web services. They enable seamless discovery, interaction, and collaboration between heterogeneous agents from different vendors and built on different frameworks. This standardization simplifies tool integration, enhances interoperability, and supports secure, structured, and asynchronous communications across different systems and domains. In essence, these protocols transform a fragmented landscape into a cohesive ecosystem, enabling AI agents and external tools to work together more effectively and efficiently than ever before. Now I'm going to walk through some of the more popular AI agent protocols, focusing on the protocols that we have been investigating. There are a lot of protocols out there, and this is a rapidly evolving landscape, so this is not a complete list, but does represent some of the more robust and complete protocols. The slides show the workflow so you can follow along there, and I'll give a description of each model and how each workflow functions, starting with the Model Context Protocol, or MCP, which was started by Anthropic. MCP is an open standard protocol for two-way communications between an LLM client and external systems or servers. Think of it like a USB-C port for external data sources. It allows agents to call other tools or agents in order to respond to queries from users. The query is the prompt given to the MCP client asking it to build an AI agent that can do a specific task. The MCP client intercepts the query and shares it with the large language model. The initial query is sent to the LLM by the client. The MCP client uses an LLM, and that LLM is responsible for generating answers based on the query and for choosing the right tool to obtain those answers. After the LLM is interfaced with, then it chooses the correct server. And the LLM sends a response to the client. Oh yeah, we did that. After the LLM sends a server selection request, the client optionally shares an approval request with the user for human-in-the-loop security. The chosen server is then used to complete the task given to it by the user, utilizing the user's query and the tool's data. After the processing is done, the result is then shared with the user. MCP is the best protocol for allowing AI assistants to access and act on real-time external context in a secure and standardized way. Agent-to-agent protocol, or A2A, was started at Google. It's an open standard protocol that defines how AI agents, even if created by different vendors or built on different frameworks, can discover, communicate, and collaborate. A2A handles agent-to-agent interoperability, while MCP enables agents to call external tools or data sources. In this example, the user sends a query to agent 1 or the client requesting a specific task or information. A public JSON file with the agent's capabilities, skills, endpoint URL, and authentication needs acts as a discovery card for clients. Through this agent card, the client discovers the capabilities for other agents, which helps them choose the best one for the current need. The task is the central unit of work. A client initiates a task by sending a message, and each task has a unique ID and progresses through the states. The server either streams server-sent events like status updates or artifacts as the task progresses, or processes the task synchronously, returning the final task object in the response. The task eventually reaches a terminal state, which is shown as the completion. After the task is completed, the result is sent back to the user through the chosen client agent. A2A is the best for enabling a network of modular AI agents to collaboratively solve multi-step real-world tasks through structured, asynchronous, inter-agent communication. Agent Communication Protocol, or ACP, is IBM's open, vendor-neutral protocol for standardizing communications between AI agents. ACP was initially introduced by IBM's BAI project and is now part of the Linux Foundation. It defines a RESTful HTTP-based wire format, enabling agents to exchange messages, assign tasks, and interact both synchronously and asynchronously. This protocol uses MCP servers from Anthropic in order to interact with cloud services. The ACP client discovers available agents such as Agent A and Agent B, shown in this example, via REST from a registry or a shared manifest. It retrieves metadata for Agent A and Agent B, including endpoints, capabilities, and security schemas, which are exposed via REST APIs. Agent A identifies Agent B's capabilities through metadata fetched from a manifest or registry. Agent A then obtains a signed capability token that defines what it is authorized to ask Agent B. Agent A sends a structured HTTP post request to Agent B with the task details and capability token. Agent B then processes the request using its LangGraph framework and possibly interacts with cloud services via MCP. Agent B then streams real-time progress results back to Agent A or to the ACP client using server-sent events. ACP is the best for enabling AI agents to work together on complex tasks, integrating legacy software, streaming data between agents, handling request cancellation, and ensuring persistency. Secure Low Latency Interactive Messaging, or SLIM, is part of Cisco's initiative called OutShift, which is focused on building the secure Internet of Agents. Cisco SLIM uses GPRC over HTTP2 as a standardized transport layer with built-in support for streaming, pub/sub, and request-response patterns. Remote agents, we are showing LangGraph and Crew AI in this example. Register securely with a central agent gateway using GPRC over the central plane, establishing identity and capabilities. The agent gateway configures both control and data planes to manage authentication, messaging policies, namespaces, and agent routing. Agents exchange messages through the gateway using slim primitives that support request response, pub sub, fire and forget, and bidirectional streaming over GPRC. The gateway dynamically routes messages between the agents, possibly including an orchestrator, applying policies and tenant isolation rules in real time. All traffic is authenticated, authorized, and encrypted with transport security via HTTP2 TLS and optionally encryption like MLS or payload level encryption. The gateway provides observability, telemetry, token rotation, and discovery services through agent manifester cards, enabling robust lifecycle and operational monitoring. SLIM is the best for composing event-driven multi-agent workflows, enabling agents to operate seamlessly across network boundaries. Agent Network Protocol, or ANP, is an open source framework that was started by the ANP team that enables efficient interoperability amongst heterogeneous AI agents. It communicates using JSON LD, decentralized identifiers, and a layered architecture for discovery, negotiation, and collaboration. In this example, we are showing a user who needs to access multiple agents in order to plan a trip. The agents are shown as a travel agent, which is an AI agent in this case, a hotel agent, an airline flight agent, and a weather agent. This starts with agent discovery. A local agent queries a discovery path, which is typically a predefined endpoint, to retrieve a list of available agents using JSON LD formatted metadata. The agent fetches detailed agent description files structured with JSON LD, which specify capabilities. The agent then constructs requests adhering to the application layer protocol standardized formats. Leveraging decentralized identifiers, the agent appends cryptographic credentials to requests, enabling end-to-end encrypted communication with the identity and encrypted communication layer. The agent transmits the requests over the meta protocol layer, which supports dynamic protocol negotiation using natural language. The agent processes requests formatted according to the application protocol layer, parsing JSON LD or similar structured data to extract and utilize the provided information or task outcomes. ANP is the best for collaboration amongst agents from diverse providers and structures in a multi-agent scenario, and is specifically designed for cross-domain agent communication and interoperability. Agora was started at the University of Oxford and is a scalable protocol enabling LLM agents to negotiate communication protocols using natural language and JSON. Agora uniquely transforms natural language requests into standardized protocols for flexible, user-centric agent interactions. This example is the same as the last one for the sake of simplicity, with the addition of a budget agent. This starts with user request parsing. A local agent interprets natural language user queries, extracting structured intent components using LLM capabilities. The agent retrieves metadata about available services, detailing their supported protocols and functionalities in JSON format. The agent then transforms parsed intent into standardized communication protocols tailored for specific service types via Agora's generation layer. The agent embeds secure authentication tokens, ensuring trusted interactions with services using protocol-defined security mechanisms. The agent then dispatches generated protocols to specialized service agents through Agora's distribution layer for task execution. Then the agent collects and processes structured responses from services, integrating results to fulfill the user's request. Agora is the best for natural language to protocol generation, allowing users to define agent interactions and workflows using natural language. Building on our discussion of current protocols, it's important to recognize the challenges that lie ahead in the development and deployment of AI agent protocols. One significant concern is ensuring security and privacy, especially as these systems are applied in sensitive domains like healthcare, finance, or personal data management. Advanced encryption techniques, robust authentication mechanisms, and comprehensive audit trails are essential to prevent malicious attacks and ensure trustworthiness in multi-agent communications. As electronic records healthcare software provider, we're following best practices for AI governance, which prioritize patient safety, data privacy, transparency, and compliance. We're establishing comprehensive oversight frameworks that define clear accountability for AI systems development, deployment, and monitoring, ensuring that AI models are rigorously validated and regularly audited for accuracy, bias, and fairness. Implementing robust data governance policies is essential and involves securing patient data through encryption, access controls, and anonymization, as well as ensuring compliance with regulations like HIPAA. Transparency is vital. We are clearly communicating to our customers, users, and patients how AI tools make decisions, including explainability features that allow clinicians and patients to understand AI-generated recommendations, incorporate continuous monitoring and feedback mechanisms, enables early detection of system errors or biases, fostering ongoing improvement. Engaging multidisciplinary governance committees, including clinicians, ethicists, legal experts, and patient advocates, can help align AI deployment with ethical standards and societal values. Finally, fostering a culture of accountability, ongoing training, and adherence to industry standards ensures that AI remains a tool that enhances patient care while upholding trust and safety in the complex healthcare environment. Scalability also remains a critical challenge. As the number of agents and interactions increases exponentially, we need scalable architectures, potentially leveraging distributed ledger technologies or decentralized protocols in order to maintain performance and reliability. Many protocols are still in their early stages, so they have yet to be widely used or applied on a large scale. This lack of maturity means that organizations must be prepared to act as early adopters and adjust to breaking changes and evolving specifications. Additionally, emerging paradigms like federated learning and edge computing can enable real-time, privacy-preserving interactions, especially in environments with limited connectivity or strict data privacy requirements. Looking forward, the evolution of AI agent protocols will likely be driven by adaptive, self-evolving standards where agents, guided by large language models and community input, learn and refine communication protocols dynamically. This approach can foster resilience, adaptability, and long-term sustainability in complex, heterogeneous environments. Ultimately, these challenges will be crucial to realize the full potential of multi-agent AI systems, paving the way for more secure, scalable, and flexible interactions that can adapt seamlessly to a rapidly changing technological landscape. As multi-agent architectures become even more relevant in multiple AI agent products and services, the need for a bridge that will allow them to communicate with each other will always be an important aspect of the entire workflow. We believe that agentic AI protocols are in their infancy and will continue to evolve rapidly in pace with the overall AI landscape. Unlike previous standards, which took years to evolve and be ratified by committees, we expect these protocols to be produced and consumed using LLM standards, emphasizing natural language and a great degree of flexibility. I've got the links for the documentation for these protocols, and I think this presentation is going to be available online. So you can take a picture of those if you want. And here's my information if you want to follow or connect on me with LinkedIn. That's a LinkedIn QR code. I don't know if it'll work blown up like that, but I tried.
Escape step to the back.
Yeah.
Perfect. We have time for a couple of questions about bulk minute. Yeah, 3 or 4 minutes. If anyone has anything, if not, we really appreciate you. The talk will be available soon. And we don't have any questions. I just want to make another reminder. Keep your badge. You'll need it for tomorrow. They won't let you that thing out is. So please have this.
Oh, and Danny asked me to remind everybody to give feedback. So I guess that you gave feedback on every single presentation or whatever, but Danny wants all the feedback. So
on your agenda for each talk, there should be some sort of feedback portal there. Please, it helps all the speakers, it helps conference. Let them know what you think. And yeah, thanks some. Thank you.
Thank you.